Hi there. So before I get started with my lecture, I came up with some kind of analog or conceptual way of trying to grasp what means coherence in terms of light and photons. So we were fooling around with Lego blocks as as we so commonly do these days with the kids, and we were building huge blocks of Lego cubes essentially by just building normal 3x4 Lego blocks, and we made a huge spheres and cubes. And there I realized that in a way how they react when they behave, these kind of huge chunks of built together cubes formed by using just simple Lego blocks, is that they in a way resembled me of how coherent versus incoherent light behaves. So if I would have, let's say, 100 Lego blocks, individual Lego blocks, and I would throw them to a wall, or I would drop them into my floor, not much of mayhem would take place because each of those Lego blocks individually, they are quite lightweight, and not much of damage will be done. I could even, in principle, don't try this at home, but I guess I could try throwing Lego blocks one at a time towards a person, and I guess that person would not be badly hurt. But of course, once I start putting Lego blocks together, and if I would have, let's say, a Lego block consisting of 1,000 2x4 blocks, it starts to be quite a bit of a piece of construction. And then when I start dropping or throwing these kind of constructions, for example, on the floor or into the wall or towards a person, then actually when this huge block of Legos actually hits the object, then a complete inferno or mayhem arises, takes place. So this is kind of, in a way, what I was thinking, that they similarly, I guess we could try what happens in the light matter interaction when we have a coherent light interacting with matter in a coherent manner, so that they all photon states that are associated with the light distribution, in a way they act in unison and together, and for example may strengthen the light matter interaction. But when we have an incoherent process, an incoherent light distribution, and then we're looking at the light matter interactions, then each of these photon states, in a way, each of these Lego blocks acts on its own. And then what we get out at the end of the interaction is that we have these kind of like more random stochastic processes that we sum together. So maybe this helps before I get started, kind of like grasping how this coherence or incoherence of light manifests itself. So maybe it would be a good idea for you to kind of think yourself what happens when you have individual Lego blocks and you throw them out into the wall, or when you have a Lego blocks joined together and you throw that huge chunk of Legos into the wall, and you can see it yourself. You right away understand that what happens is quite different in these two different scenarios. So otherwise, nothing strange much will happen, and in other case, you have a complete Lego inferno and a dent in the wall. So maybe this kind of analog helps, because here, of course, we're speaking about diffraction, and here we're implicitly assuming that we have complete coherence in the fields, because we're mindlessly summing the fields together and computing the superimposed fields, calculating them, and then calculating the irradiance patterns. And there, we don't explicitly say that, but we are implicitly assuming that we have perfectly coherent light distributions that we are operating with. And this is what I wanted to kind of nudge you towards thinking about yourself and asking questions from yourself and friends and us teachers, that how these things could be understood. And now to the actual topic. So I will be speaking here about diffraction from multiple slits. So in the previous lecture, we started to understanding everything there is to know about diffraction from basic aperture shapes. And now we're just basically taking some of those shapes, we meaning consider here a single 1D slits, and then we arrange them periodically, and then we look what kind of superimposed fields we get out with this kind of configuration, and essentially what kind of irradiance distributions we get. So this is basically providing us means to calculate how a diffraction grating behaves. A simple diffraction grating, a singly periodic diffraction grating. So this is what I will be speaking about during this lecture. So we will consider an aperture configuration that consists now of several and this is the key, periodically arranged slits along the x direction. And a single slit, we understand how that behaves. So now instead of a single slit, we now just have many, and they are periodically arranged. The width of the slit, let's denote that still with a parameter a, so that the terminology remains the same, and the separation of slits is now b. Maybe it should be the kind of like a other b, so as in period, but let's try to remember that this is b as in period, and this is the kind of new parameter into our calculation. And along the y direction still, of course, no diffraction takes place, and this is fine. And the only thing we need to consider is that we need to consider what happens along the x direction. And this basically, we now need to extend our former integral into actually a series of n diffraction integrals. So mathematically, this problem statement now looks like this. So we are now summing n slits. It's not just a one slit, and this is basically the integral that we solved previously for the case of a single slit. And now we need to also adjust the integration variable accordingly and the limits so that we can properly sum all of these different slits together. But essentially, this integral, this is providing us the kind of summed field arising and the diffraction arising from a single slit, and now we're just summing over the contribution of all the slits that we are considering. So this is basically what we do here. And here we have still the summation, and now we can chunk in what we have solved for the case of the single slit already. So we know this, we can copy paste this from the previous lecture. So we have basically, we are summing now terms that are minus r divided by ikx, and then we have the brackets that we have the kind of something resembling a sinusoidal function, essentially exponents of a strange looking character. And now we can separate things, so we can actually take out something inside the square brackets, and I will do this now and I will explain later. So essentially I can take this term out, so the exponent ikxn b/r. So this is how I can simplify things. So I can take the first term here out away, and only thing that is left here inside the square brackets will be this a/2, plus of course the other parameters in the exponents. And this of course helps out my treatment in what follows. So I have this kind of formula now, and essentially this is providing us the diffraction pattern associated with the single slit, and now we are summing many patterns, and then we have this kind of additional phase term involved in the summation. And let's see if I can actually do that. I will first show some results, how things will look like, so that we are considering this kind of 1D slits, and they are periodically arranged, and the diffraction creating period b now is basically this distance shown in here. So this is the geometry, and here in the b figure I'm showing the cardinal sine squared behavior. So this is kind of an overall curve that defines how the diffraction pattern will look like, and this is essentially dictated by the single slit diffraction. And this will be what we are getting out due to the fact that we're actually summing many contributions, and then these E and F figures are showing the total overall distribution of the irradiation when we have put all of these different terms together. So essentially here what we are seeing is that when we change the number of slits into a higher value, so n, that was the kind of index that we are summing over the terms, these individual peaks, they become narrower, as you may be able to verify yourself by comparing the figures E and F together. So this is essentially what I will be aiming at. So I will be wanting to calculate the irradiance distribution of this periodic arrangement of one-dimensional slits. So this is the equation. And like I said, the term inside the angle brackets, that's the diffraction corresponding to a single slit. So this we can already solve, and that essentially provides me a cardinal sine type of a function. And that's it. And let's now look how we can solve the actual summation. And we can do that quite easily by redefining a variable, beta. And this beta, do not get confused this with the case of the rectangular function. This has nothing to do with that beta. So let's just define that the beta is k times x times b. And that's the reason why I'm using beta here, because I had this b parameter here. And then I'm dividing with the 2r here. And now the sum term, we can really reduce that quite easily. So we have this kind of summation term here. Essentially, we are turning this into something that looks cleaner. And then this is essentially forming a geometric series. And now it's not forming a series until infinity, but rather it kind of ends abruptly at some point at the index of n-1. So we're really like dealing with a partial summation of a geometric series. And then we can really solve that quite easily by just looking at the Wikipedia, what is the solution, and then we get the right solution out. So essentially, this is for the case of a geometric series of exponent. We have 1 minus the parameter in the geometric series. Usually we denote that with the r. So r to the power of n, and then we divide that with the 1 minus r itself. So essentially here, like we are using exponent minus I to beta as our r parameter in the geometric series, and we are doing a partial summation. So that's how we get into here. So this is actually like a pretty simple geometric series application of that into an exponential function, but there is this one slight trouble that the usual geometric series is being defined for a r parameter that has a modulus that is less than unity. And here we can see that we actually in fact have a modulus of unity. So we are not really strictly speaking dealing with a convergent series anymore, but rather it's a divergent series. So mathematically we are in trouble here, so that we should be careful. But we are physicists, we are proud physicists, so we do not really care. And as long as we can kind of calculate something out, a finite value, we do not care that much that, like pedantically speaking, this kind of series would actually be a divergent. But as long as we're happy of finding out, calculating the solution out as a function of n, we're fine with that. But please note that when we would be extending this n towards infinity, this series would not converge to a single value, but rather it would be oscillating between two different points. So that would be the trouble here. So it doesn't converge, so it doesn't diverge into infinity, but rather it never just converges, but rather it keeps on oscillating between two different solutions. So that's quite peculiar for this kind of particular example. But we're physicists, we're happy with this. We have solved the summation, and now we can like progress things further. So we can take common multipliers out. So at the numerator, on the top side of the fraction, like I can take this kind of term out. And now, of course, I'm multiplying this with the I and beta term so that I get unity out. And then I will get this into a cleaner form, as we can quickly see. So essentially, I want to cast my numerator into a form where it's looking like a sinusoidal function. So exponent of a sinusoidal. I'm just missing the 2i here on the denominator. So and this I can do by just taking this term exponent my n beta as a common factor. So if I would be multiplying this into this, I would be getting unity out. And if I'm multiplying that with this guy, then I'm getting this minus exponent I 2n beta term. And I will do the same thing here on the denominator. So I will take this kind of term out, and then I will have the conjugate of that as the first term. So exponent I beta, and then minus exponent minus I beta as the second term. And now I can see that if I'm multiplying this guy with this, I'm exactly getting this guy out. So all is fine. And now I can cast these two terms into signs, and nicely for me the two i's vanish, so they cancel each other out. So what I'm left is that I have this exponent, and then I can write that as a single exponent. So I'm just subtracting this minus beta here out to get this form, and then I have the signs of n times beta divided by sine of a beta. And here this is the crucial thing here. So we have n, that is the number of slits in my diffraction grating, or periodic arrangement of slits that is inside the first sine argument. So here if I increase n, then this phase argument here, the argument of the sine, starts changing more rapidly. So of course this will give me the kind of possibility that the peaks, the irradiance peaks, become narrower as a function of the capital N. so the number of slits. So I have now means to calculate what is the diffracted field, and the diffracted field along the x direction, Ex, is basically proportional to A, and this is a term that we get out when we cast this exponent into a cardinal sign. So I have this A here, so I definitely need to also have this A here, and then I need to multiply also the denominator, and that's why we are now left with A in here. And the left, this summation we just calculated, so that we can now cast into this sine n beta divided by sine beta. And please note, this is not actually a cardinal sign function, but rather two signs in a fraction. And the corresponding irradiance, of course, we can just take the modulo square of this field, and then we get something. So we had the irradiance distribution with respect to the capital X coordinate, so that we normalize that to the central location of my diffraction pattern, so I0, where the X is 0. And then I have the cardinal sign of alpha term, and this corresponds to the diffraction from a single slit. And then I have the second term that is now the sines of n times beta divided by sine of beta, and this squared. So the first term will be basically, like I said, the diffraction corresponding to a single slit. So it gives us a kind of like overall smoothness for the irradiance. And then the second term is actually due to the periodic arrangements of slits. And now we can look at the figure again and see what we have just done and shown. So this is the overall smooth curve arising from the single slit factor. So this is the cardinal sign squared. And then I have these diffraction profile arising from the periodic arrangement of slits. So here the case for N5 and here for the case of N10. So this is basically, I'm plotting now the square of the sine n beta divided by sine beta. So I'm getting this kind of term out. And when I'm multiplying that with the cardinal sign squared, I'm getting the overall diffraction profile out. So essentially what I'm seeing is that I start seeing many peaks in here, and this is basically how a diffraction profile looks like from a diffraction grading structure. And before I stop here, maybe I should point out for the people who are curious that in previous chapters we were mentioning about this optical path length and the principle of least action, that the ray of light wave takes the path where it takes the smallest amount of time, or stationary path. It takes the stationary path for light. And now for the case of a diffraction grading, light doesn't anymore like go through a single path, but rather there actually may be many possibilities. And in a way, like if it would be generalizing the concept of calculating what happens for light using the kind of optical path length difference, making a functional out of that, and then calculating the stationary paths, I would be able to see many minimas in that, essentially, so that now each of those minimas would correspond to each of these diffraction gradings. So in a way, like if I would be thinking that light goes through all the possible paths there is, these specific directions into which light is being diffracted, there the optical path lengths is become stationary. And then these paths, we will end up having constructive interference between the different paths, and then I will actually be getting also a constructive interference. And between the directions, I'm actually having destructive interference, and these are the paths the photon doesn't take. So in case you're kind of interested in quantum mechanics or quantum field theories in connection of optics, and ultimately I think everybody of us should be, at least I am, and there, like the Feynman formulation of path integrals in order to understand what happens for photons, I think it's quite elucidating and very neat, and it's very elegant and beautiful. So here, this is what I wanted to say, and please also ask yourselves, like if I would come with a single one photon at a time, would I see these kind of diffraction profiles emerging? And of course, the answer would be that yes, I would, as long as we're dealing with linear optics. the outcome of my experiment doesn't really change. Do I do it 1,000 photons at a time or 1 million photons at a single time? I will see a diffraction pattern forming. Or do I do 1 million experiments where I'm coming with a 1 photon at a time and I'm recording the subsequent outcome of my experiment? So the outcome will be exactly the same. So we see that these kind of diffraction peaks and constructive interference versus destructive interference also takes place for individual photons. And this, I guess, is a kind of like a thought experiment. A fancy word I can use, Gedanken experiment, is that I think we should all ask and try to structure the understanding that we have out of optics in our minds so that we would be able to get the right answer. And the right answer is that nothing will be changing in terms of linear optical interactions when we are coming single photon at a time or 1 million photons simultaneously. So I stop here. I hope you enjoyed and I hope the lecture was clear, and please join me shortly when we are actually going through the more general things regarding diffraction gratings. We now understood perfectly how they behave. So thanks and have a good day. Bye.